Hello everyone, welcome to another robotics session. So far we learned how to drive forward kinematics and also calculate the velocity of a robot's end effector. Now as I said, the interesting problem is actually the inverse of forward kinematics, inverse kinematics. We're more interested in knowing the joint angles or joint translation as a function of robot end effector position. Why? Because when we want to perform a task, for instance, move this pen using a robot, we usually use sensors such as cameras to measure the position of this pen. Then the robot needs to come and pick this pen. So the position of the robot end effector, where we want it to be, is known. Now we need to calculate the inverse problem. What should be the joint angles to get here? Today, in this session and the next one, we're going to talk about some interesting features of Jacobian matrix that will give us an insight into how to solve the inverse problem. Well, as I mentioned, inverse kinematic includes calculating the robot joints angles or displacement as a function of robot end effector pose. For the forward kinematics, we already know how to get position and orientation of robot from its joint. And we said the task space dimensionality is usually shown by n and joint space by n. The inverse kinematic problem is actually inverse of this, assuming that we know end effector position and orientation, and then how can we calculate the joint angles? One thing is that this obviously sometimes doesn't have an answer. Consider a case where we have a robot that is under-actuated. Previously I mentioned that the robot that's under-actuated has less degrees of freedom than required to do a task. Consider this two-link serial robot. It has 2 degrees of freedom, 2 rotary joint angles. If we write the equations for forward kinematics, it would give us the xy position as a function of the 2 joint angles. Now what if we wanted to perform a task in 3D? Our goal was to manipulate an object in 3D. And we wanted to reach a point with desired x, y, and z position, even at an angle. Forward kinematics is similar, but is it possible to do the inverse? Can we calculate theta 1 and theta 2 knowing x, y, z, and phi? It might be not possible. The fact is that this is a 2D robot and it cannot get into 3D. So if we had a z value that was not 0, let's say 0.1 meter outside the plane, the robot cannot get there. The solution doesn't exist. This is the case of under-actuated robots, when we don't have enough degrees of freedom for a task that's more demanding, has more degrees of freedom. When m is bigger than n. In this case, solving inverse kinematics is not always possible. So there's another case when we have a robot that's fully actuated, like this robot. This robot has 3 links, A1, A2, A3, and has 3 joints. Let's say we want the robot end effector to be at this position shown by blue. The forward kinematics would give us the x, y, and angle of the end effector as a function of the 3 joint angles. Let's call them theta 1, theta 2, theta 3. Now if we have a specific point, we know x, y, and the angle for it. Can we calculate theta 1, theta 2, theta 3? The solution might exist, it might not. It really actually depends if that point falls into the workspace of the robot or not. For this specific point, the blue point, there might be two configurations like shown in the figure, like one with the dashed line and the one with the solid line. Both of these configuration spaces have different theta values but give the same end effector position. So this makes solving inverse problem more complicated. For some points it might not be even possible. If we assume the distance between these two joints are W for this case, if W is bigger than length of link 1 A1 plus length of link 2 A2, there would be no solution at all. If it's exactly equal to these two values, then there would be only one solution, and if it's smaller, there would be multiple solutions. So you can get an idea about how difficult inverse kinematics is, and even for a fully actuated robot, we might have difficulties getting it from forward kinematics. That's why we usually don't look at forward kinematics. We look at the Jacobian and velocity kinematics. Consider the same robot that has 3 links and 3 joints fully actuated. Instead of looking at the forward kinematics, let's take a look at the velocity kinematics. Previously we shown that the end effector position velocity of the end effector can be calculated using a Jacobian. Now can we use this equation to estimate the inverse kinematic? Remember, inverse kinematic is finding joint angles as a function of end effector position. This would be an easier task, and the fact is that we can do it by taking the integral of the inverse of this equation throughout time. If we take the inverse of this equation, q dot would be Jacobian inverse times x dot. Then we can simply use this equation, assume we know x position and we want to go to a desired x position. We can calculate an x dot, take integral of this equation to find q, and see if we're there or not. If not, calculate the integral again knowing our position. So q would be integral of j inverse x dot dt. And we can repeat this from any position to any position until we get there. So this shows the same concept. Knowing the velocity kinematics, we can take the inverse and repeat the process by every time calculating the difference between desired position and actual position in order to update q and hope that we can iteratively calculate the quotient and get to q. This method is very problematic. This would be the easiest way to get the inverse kinematics, but you can guess where would the problem be. First thing that shows up is that this process is very time consuming. You have to repeat this process iteratively to get to a point. The second thing is Jacobian invertible? We assume we can estimate inverse of Jacobian, but can we actually estimate inverse of any matrix? Look at this simple Jacobian. This is a Jacobian for a 2-link robot that has 2 joints. And it's shorthand notation. S1 shows S of theta 1, and this would be S of theta 1 plus theta 2. Assume we have this Jacobian. Can we find the inverse of the Jacobian? From linear algebra, probably you can remember that inverse of a 2 by 2 matrix is given by this equation. And it is fully invertible when the determinant term here is not 0. If this is 0, you cannot define an inverse for this matrix. So this shows that even for a fully actuated robot that we have a square Jacobian, there might not be a solution to the inverse problem when the Jacobian is not invertible. For this case, you can probably solve it and see when the Jacobian is not invertible. Use this equation to find the inverse and calculate the inverse. The determinant term should show up like this, and you can see when this is 0, then Jacobian will not be we cannot define the Jacobian. And when this term 0, when the second angle of the robot is 0. Look at this picture and see where the inverse does not exist. This is the 2-arm robot, and in a scenario where the second angle is 0. Based on the inverse of Jacobian, we realize that at this specific configuration, the Jacobian is not invertible, and we cannot calculate inverse kinematics. But does it have any physical meaning by looking at it? Does it have any physical meaning? What does it mean we can't calculate the inverse Jacobian and the inverse kinematic doesn't exist? But if you look at this case, at this specific point in time, when the angle here is 0, the robot cannot move forward. There's no way, there is no possible motion that could lead the robot to go forward. It will always be in exact perpendicular direction. What does it mean? It means that one of the degrees of freedom is suddenly lost. The robot that previously was able to move in XY plane freely, now at one specific point cannot move forward. This is a concept in robotics we call singularities. And in serial robots it might happen a lot, even if you consider your arm. If you consider these two as link 1 and link 2, when this joint is 0, there is a singularity in your arm. You cannot move this joint and this joint at this instant and go forward. There's no possibility. As soon as you move, it goes upward. For a specific point, you've lost a degree of freedom in your arm. This is what's called singularity. Singularities in robotics are important. They usually must be avoided. These are the exact moment during a robot's motion where there's a good chance that we could damage a robot. Consider your arm again. At a singularity, it cannot move forward. Now what happens if suddenly somebody applies a force to your hand at this configuration? Your hand cannot move in that direction. There is a chance that this joint will break. In robots it happens a lot, specifically if it's interactive environment. If it's at a singularity position and then suddenly a force forces it to move in a degree of freedom that it cannot move in, it would break. So it's important to identify singularities and avoid them as much as possible. Singularity can be easily realized by looking at the Jacobian matrix. A Jacobian matrix is an M by N matrix, where N is number of joints, M is the task space dimension. If rank of matrix J drops, we have a singularity. What does it mean, rank, and when it drops? Rank of a matrix drops when a matrix determinant is 0, as we showed. In other terms, if we want to give it another definition, rank of a matrix drops when two columns or two vectors in the matrix are linearly dependent. Look at the matrix like this. If you look at this matrix, this column and this column, if you add them up, you will get this column. Therefore, the third column is dependent on the first two. It's a linear function of the first two. This is a 3 by 3 matrix, but one column is linearly dependent on the other two. Therefore, rank of the matrix J is 2. It's not 3. So rank is basically the number of linearly independent columns or rows of a matrix, and it's almost always is equal to minimum number of rank and rows. So for a matrix that has J m by n, its rank is always minimum of m and n. If J is a 2 by 3 matrix, its rank is always 2. Sometimes it's hard to understand what is linear independence. A good way to understand it is to look at the Jacobian as a map. When we write the forward velocity kinematics, where we get the robot end effector velocity as a function of joint velocity, this is essentially a mapping. This mapping maps joint inputs into end effector velocities. And a mapping is defined by a matrix. Each column of the matrix shows one direction for the map. If a matrix has these three columns shown here, A, B, and C, these are directions that our matrix A, B, C can map joint inputs in those directions. If any of these two directions are linearly dependent, that means they are in the same plane. Therefore, the Jacobian cannot map it in outside of this plane. For instance, this case, A, B, C are all in one plane. So the Jacobian can only map motions in this plane. If you want to use this robot for a 3D task, it could not come out of plane. This is what rank and losing rank for Jacobian means. Suddenly the robot gets stuck in one plane or reduces its degrees of freedom, and it cannot do something that it could do before. When the Jacobian is full rank, like in this case, we have three vectors in the Jacobian that can map the joint velocities in 3D space. Recap: by looking at Jacobian, we can get useful information about the robot's motion. By looking at its rank, for instance, we can estimate whenever the rank drops, it won't be invertible. That is a case where robot is losing degree of freedom, and we call that a singular position. By analyzing the Jacobian, we can estimate these singular positions.